For decades, owner-operators ruled the asphalt. They tuned their own iron and answered to no one but the deadline. Then, the rules changed overnight. The government mandated crushing weight limits and a hidden digital black box designed to track every single mile. The friendly rivalry of the truck stop instantly mutated into a total corporate war. While fleets were paralyzed by boiling coolant and cracked cylinder heads, underground mechanics fought back, unlocking monstrous power with nothing but a screwdriver and a highly guarded secret tuning ratio. This is the story of how Caterpillar, Cummins, and Detroit Diesel went to war to survive the Silicon Era, and how the unbreakable mechanical heart of the American truck was systematically destroyed. On January 6, 1983, Ronald Reagan signed the Surface Transportation Assistance Act. The STAA was sold as an infrastructure fix. For the men behind the wheel, it was a total overhaul of how the road worked, and what the engine under the hood had to survive. The law mandated that states allow 48-foot trailers and established a uniform federal weight limit of 80,000 pounds across the newly designated national network. Overnight, the highways filled with walls of iron, massive trailers moving at full weight simultaneously on every interstate. Before 1983, every state had different rules. Drivers had to carry smaller loads or drive hundreds of miles out of their way just to stay legal. That inefficiency vanished overnight, and suddenly every truck was legal to gross maximum weight on every interstate and major primary route in the country. The real vulnerability, though, sat in the engine block itself. The 3208 V8 was supposed to be CAT's answer for fleet buyers, cheap, simple, and fast to build. But CAT used a parent bore block, which meant the piston rode directly against bare cast iron with no replaceable cylinder liners. When that surface scored, the block went straight to the scrap heap. Mechanics called it the throwaway engine, and the label stuck. The company that built the legendary 3406B had also built an engine you threw away. And fleet managers couldn't help but wonder, if they'd cut corners on the 3208, where else had they cut corners? The iron under the hood wasn't built for this. These engines were designed for a different world, where loads were lighter and grades weren't as punishing. Thermal stress on these blocks climbed fast. You couldn't just turn up the fuel and keep rolling, because the cooling systems weren't designed for a sustained high-load heat at 80,000 pounds. Cummins had the most to lose, because they controlled about 60% of the market back then. But they were about to learn that trying to cheat the laws of heat can destroy a market share like that in a single summer. Their main weapon was the 14 liters Big Cam series, and the Big Cam 3 was the undisputed fleet standard. Mechanics loved working on them, and owner-operators trusted them to achieve legendary longevity, a million-mile service life after a single midlife rebuild that set the industry standard. The pressure-time fuel system was simple enough to tune with basic hand tools, and that massive 2.5-inch camshaft made it one of the best fuel delivery setups in the business. But the Cummins board was feeling the heat from two different sides. Japanese manufacturers were undercutting prices so hard that Cummins slashed their own rates by 40% just to stay in the game. That move destroyed their margins, which meant R&D budgets got cut and timelines got squeezed. The Big Cam 4 was rushed to market under conditions that no real engineer would ever sign off on. To handle the heat of the new 80,000-pound limit, Cummins introduced something called optimized aftercooling. The idea was to slow the coolant down so it spent more time in the radiator shedding heat before returning to the block. They used dual thermostats and internal flow restrictors to create a complex system that was supposed to squeeze every bit of efficiency out of the 855 block. In the real world, the system collapsed. When a driver hit a sustained pull in the summer heat of the San Joaquin Valley, the coolant didn't move fast enough to keep up. Localized boiling started in the water jackets, creating vapor pockets that hit the metal with thermal shock, and you could hear it, that metallic crack and ping as the head warped. Cummins dealers were soon stacking up cracked cylinder heads like cordwood, and every cracked head meant a $20,000 rebuild bill that the fleet never saw coming. Specialty shops like Pittsburgh Power made a fortune ripping the low-flow systems out and converting them back to the old high-flow specs with custom radiators and high-capacity pumps. Fleet managers who had bet their business on Cummins' reliability weren't just furious, they were bleeding cash. But the mechanical failures were only half the battle. The new law forced a complete change in how an engine was supposed to work. Freight rates were collapsing and diesel prices were climbing, so fuel mileage became a matter of survival. And trucks weren't just fighting each other for that freight anymore. The railroads had figured out intermodal, loading truck trailers directly onto flat cars and moving them across the country for less money per mile than any diesel could match on the open road. If a fleet couldn't prove its trucks were cheaper to run than a railroad container, shippers would put the freight on a train. Fuel economy stopped being a selling point and became a survival requirement. Cummins pushed their formula engines and Detroit Diesel sold their fuel squeezer models. Both designs forced the driver into a lower RPM range where the torque lived, rewarding lugging over revving. The guys behind the wheel hated it, gutless trucks that felt like they couldn't climb a hill. What they didn't realize was that the torque was still there, just sitting lower in the rev range than they were used to. While Cummins was busy pulling cracked heads and Detroit was bleeding market share, Caterpillar was watching from the sidelines. They had been in the earth-moving business long enough to have already solved the problem that was killing their competition. You don't build a D9 bulldozer without understanding sustained heat under load, and what they learned in the dirt transferred directly to the highway. CAT was running two completely different philosophies under the same roof. One produced a budget engine that fleet accountants loved and mechanics cursed. The other quietly assembled the most durable highway power plant the industry had ever seen. The same company that gave fleets the throwaway 3208 also gave owner-operators the machine they'd still be rebuilding 40 years later. In 1983, CAT released the 3406B, which featured 14.6 liters of inline-six displacement and a deep skirt cast iron block with replaceable wet cylinder liners. The 3406B was a brute force solution to a thermal problem that had crippled every rival, but it held a secret the Caterpillar boardroom never intended for the driver to find. The heart of the machine was a scroll-type mechanical fuel injection pump that was precise and tunable, and it required zero electrics to keep the truck moving. That pump was also a mechanical loophole that could turn a standard freight hauler into a mountain climbing monster. All it took was a lead wire seal and the specific knowledge that only a handful of men possessed. They rated it between 310 and 425 horsepower from the factory, though military variants pushed all the way up to 600. The torque curve was wide and flat in all the right places, which mattered more than peak horsepower numbers on a spec sheet when you were pulling maxed out iron up a Rocky Mountain grade. The key to separating the 3406B from everything Cummins had tried was air-to-air aftercooling. Instead of routing the turbocharger's hot compressed intake air through a coolant-based heat exchanger, CAT mounted a dedicated charge air cooler in front of the main radiator, so moving air from highway speed passed through it directly. The air cooled down fast before it hit the engine. This meant thick, cold, powerful air filled the cylinders on every stroke, regardless of what the thermometer outside read or how heavy the load climbed. And it did so without dual thermostats, flow restrictors, or complex plumbing that could fail on a mountain pass at midnight. The block itself was built to be rebuilt forever, and when a cylinder liner finally wore out, a mechanic just dropped the oil pan and pulled the piston to slide the old liner out. He dropped a new one in and put it back together, which effectively reset that legendary longevity all over again. A well-maintained 3406B simply refused to die. Mechanics talked about rebuilding them 2 or 3 times like it was a normal afternoon job. The iron was just that good. An engine that lived 300,000 miles past its first overhaul didn't just earn its keep, it paid for itself 2 or 3 times over before it ever needed to be replaced. Owner-operators figured this out fast, and the 3406B became the engine of the large car culture. The Peterbilt 359, the Kenworth W900, and the long hood trucks that dominated independent trucking in the 1980s all ran cat yellow. Underneath that culture was a specific character who made the 3406B something more than a reliable freight hauler: the pump man. Every truck stop ecosystem in the 1980s had one, and he was the diesel injection specialist who understood the 3406B's mechanical governor the way a surgeon understands anatomy. The factory sealed the fuel rack to keep people out, but a skilled pump man knew how to balance the fuel and torque screws to unlock massive power without melting the pistons. The ratio that circulated in the shops was 1.5 turns on the fuel screw for every 1 turn on the torque screw. That specific combination pushed fuel delivery hard enough to wake the engine up without blowing the ring lands out. Too much on the fuel screw alone and the pistons cooked. Too conservative and you'd left horsepower on the table. Getting that ratio exactly right was the difference between a tuned engine and a blown one, and the pump men who knew it guarded the knowledge like a trade secret. If you got it right, a factory 350 horsepower 3406B became a 500 horsepower monster without a computer or a diagnostic port. The result was black smoke so thick it choked the truck behind you, and a turbo whistle that screamed against the red line, pushed past factory limits by nothing but mechanical leverage and a driver's will. On a grade, that meant pulling away from a factory-rated truck like it was standing still, the tuned engine still hungry while the stock truck was gasping for air. A pump man who understood that ratio had access to power that the boardroom never intended to give him, and every owner-operator who ran one knew it. That was the public face of Caterpillar in the 1980s, representing the bulletproof engine and the million-mile standard. It was the driver's machine. But the private face was the 3208. The 3208 was a 10.4-liter V8 designed for the fleet accountant who needed cheap diesel power. Mechanics called it the throwaway engine, and the label stuck hard. It put a dent in the armor that the 3406 had built. Then there was the retarder war. Jacobs Vehicle Systems had owned the compression-release engine brake market since 1961. Cat tried to kill it with a brake saver, a hydrodynamic retarder that dumped its heat straight into the coolant loop, overwhelmed the radiator in sustained desert heat, and left silica deposits in the passages. Drivers rejected it. Cummins eventually released the C-brake once the Jacobs patents expired, but Jacobs survived on brand loyalty alone. To an American trucker, a compression brake was a Jake, and that name wasn't going anywhere. Cat and Cummins were so deep in their own problems, cooling failures, retarder wars, cracked heads, throwaway blocks, that neither of them saw what was coming out of Allentown, Pennsylvania. By the time they looked up, Mack had already crossed a line neither of them had come close to. While Cat was printing money on the 3406B and Cummins was trying to undo the low-flow damage, a company out of Allentown, Pennsylvania was building something that made both of them nervous. Pure displacement, pure torque, a sledgehammer wrapped in black paint with a gold bulldog on the hood. The Mack E9 V8 was 16.4 liters of twin-turbocharged, 4-stroke power plant configured in a 90-degree V8 that measured nearly 1,000 cubic inches. The firing order alone produced an exhaust note that rattled windows and registered in your chest before your ears even processed the sound. That deep, loping rhythm was nothing like the inline-six thrum of a 3406B or the tight mechanical cadence of a big cam, and it sat in a different category of sound entirely. It was lower, slower, and much more violent. When an E9 crested a hill, you didn't hear it arrive, you felt it. The whole machine vibrating with a kind of mechanical certainty that no other engine on the highway could match. In 1985, Mack broke through the 500 horsepower barrier with the E9 in commercial production, and that number needs some context to understand. At that point in the history, 400 horsepower was considered serious iron for a highway truck, and 500 horsepower was usually reserved for mining equipment. Factory numbers didn't reach that high in a street-legal rig. But Mack put it there anyway, and the rest of the industry had to reckon with it. To fit that massive engine under a hood, Mack had to redesign the truck around it, which led to the Superliner 2. The cap was raised and the hood squared off to breathe for the twin turbos and the massive front-mounted charge air cooler. The result was one of the most intimidating profiles ever to roll down an American interstate. Mack marked the launch with the 1985 Magnum Edition, a limited run of black trucks with red lettering and aerodynamic stripes, split between the Superliner 2 conventional and the Ultraliner cabover. With production capped at just 250 units, the allocation was fiercely limited, and dealers fought tooth and nail just to get a single one on their lot. The Magnum Edition didn't need to fire up to shut down a truck stop. The profile alone did the work. That squared-off hood, the raised cab, the twin stacks sitting wide, you knew what it was before the key turned. The torque figures that came with the E9 were not theoretical, and at full gross weight, that low-end output hit drivelines hard enough to expose every weak point in a truck's powertrain. Careless clutch engagement shattered clutch packs, and an improperly loaded gear selection could twist the steel drive shaft into scrap. The E9 had no patience for sloppy operators, and it punished the absence of skill immediately. But if you put a precise driver behind the wheel, the physics worked in your favor in a way no inline-six could replicate. The sheer mass of the rotating assembly and the width of the torque band created a fundamentally different mechanical experience. Operators who understood it described a pull that the more efficient six cylinders couldn't match, like the engine was always holding something back, never fully extended, never at its limit. Those reserves got tested in the Australian outback in ways no American highway ever could. Australian road train operators were moving configurations that reached 200 tons on unpaved dirt tracks, hauling thousands of head of cattle across the continent. And the iron they trusted to do it was Mack. The E9 was one of the few power plants that could sustain that thermal and mechanical load without catastrophic failure. In the 120-degree heat of the Northern Territory, an engine failure wasn't just a delay, it was a life-threatening event. Choosing the wrong engine was a survival problem rather than a warranty issue. Mack built the whole truck themselves, the engine, the gears, and the axles. Because everything was designed to work together, the truck could survive heat and loads that would have snapped other trucks in half. The gold bulldog on the hood told you exactly what you were looking at. The whole truck was Mack, from the firewall back, one unbreakable unit. Every component was rated for the torque that engine could produce, and that bulldog told other trucks on the track this machine is not going to break, and it's not going to stop. No mismatched components, no torque curves the axles weren't rated to handle. Mack had engineered the machine as a single system, not as a collection of parts hoping to survive together. The emergence of the E9 forced a philosophical line to be drawn across the entire industry. On one side was the old two-stroke philosophy that told you to push the RPMs and keep the blower spooled. But on the other side was the four-stroke torque rise doctrine. Cat, Cummins, and now Mack had all committed to this from different directions, choosing massive torque at the bottom of the rev range over high RPM at the top. The screaming Jimmy was a hare that needed constant attention and high revs to stay alive. The E9 was a tortoise, and you just put the load on it, left it in gear, and let the unstoppable momentum carry you forward. By the end of the decade, the market had delivered its verdict, and the hare was dead while the tortoise had the highway. But while Mack was building a fortress in the outback, the original king of the American highway was facing a total collapse. By 1987, Detroit Diesel was a ghost of the powerhouse it used to be. Back in the early 70s, the company owned 41% of the heavy-duty market, but by the time the GM accountants finished their audit in the mid-80s, that share had cratered to about 3 or 4%. The division was burning through its warranty budget while building engines that the market simply didn't trust anymore. GM had poured money into almost every other branch of the business, leaving Detroit Diesel to survive on a budget so thin that their capital for the entire decade was only about $100 million. When you compare that to a $50 billion corporate modernization program, it isn't an investment, it's a holding pattern before the GM accountants finally pull the plug. The two-stroke engine made Detroit Diesel famous, but now it was the weight dragging them under. The Roots blower had to spin constantly at high RPM just to push exhaust out and pull fresh air in. And when the EPA started setting hard limits on what came out of the stack, the two-stroke had no answer. You can't engineer your way out of a fundamental flaw in the breathing cycle. The EPA's 1988 emission standards wrote the obituary. Detroit managed to keep the two-stroke on life support with electric Band-Aids for a few more years, but as the brutal 1994 standards loomed, the front office finally accepted what the physics had been saying all along. The two-stroke highway engine was done. And Detroit wasn't alone in its misery. International Harvester had spent the early part of the decade fighting its own near bankruptcy, eventually shedding its agricultural division and reorganizing its surviving truck operations into Navistar International by 1986. Their DT466 was holding ground in the medium-duty and vocational market, but on the long-haul side, Navistar was scrambling for the same fleet dollars that Cat, Cummins, and Detroit were all bleeding to keep. The entire industry was in triage, and nobody had enough cash to fix the problem the right way. Roger Penske saw the situation differently. Where the GM board saw liability, Penske saw engineers who had been starved of leadership and cash, not talent. In January 1988, he took 60% of the company and full operational control, spinning the heavy-duty operations into the independent Detroit Diesel Corporation. His first changes at the Redford plant didn't involve the engines. He ordered the shop floors scrubbed and painted white. Same principle he used at his IndyCar pits. A leaking part is visible the second it comes off the line. A sloppy mistake has nowhere to hide. Precision wasn't a goal, it was the baseline. The engineering fix Penske needed was already sitting inside GM before he even took over. The Series 60 was a clean-sheet four-stroke inline-six that used a single overhead camshaft, which was a setup you almost never saw in heavy-duty trucking back then. By putting the camshaft right in the cylinder head, they got rid of the long push rods found in older engines, and this allowed the electronic injectors to hit pressures high enough to turn diesel into a fine mist. That mist burned so completely that the engine ran clean without any mechanical backup or secondary governor. The engine lived and died by the ECM, and it required that electronic control module to function at all. Detroit made electronics mandatory for the iron to function at all. The Series 60 couldn't run without its ECM, which meant every owner who bought one was dependent on the system, the software, and the dealership behind it. Cat and Cummins realized they'd been outworked before they even knew they were in a fight. The Series 60 didn't just steal customers, it showed the world that Cat and Cummins had completely misread the future. Both of those companies spent the 80s trying to perfect mechanical fuel injection right when the law was making those systems obsolete. The EPA's 1988 rules weren't a suggestion, and they set hard limits on soot and nitrogen oxides that a mechanical pump wouldn't hit without ruining the engine's performance. And 1988 was only the first wave. The 1991 standards tightened the NOx ceiling further, and by 1994 the EPA had cut allowable particulate matter so deep that any engine still running a purely mechanical injection system was effectively illegal for new production. 3 rounds of mandates in 6 years. The industry didn't get a chance to breathe between them. The physics of the cylinder created a brutal trap. Run the engine hot to burn the soot and you create NOx. Cool it down to kill the NOx and the soot comes back. A mechanical governor can't resolve that trade-off on the fly. To hit the 1988 limits without a computer, engineers retarded the injection timing, spraying fuel later in the stroke. Combustion burned longer, heat went into the radiator instead of the crankshaft, and fuel mileage tanked. The throttle felt soft and unresponsive. Drivers who had spent 20 years trusting their iron stepped on the pedal and felt nothing come back. Caterpillar tried to fix this with a system called Peak. They basically bolted an electronic control module onto the old 3406B mechanical pump instead of building something new. They used electronic actuators to move the fuel rack, hoping to get digital precision while keeping the mechanical bones that made the 3406 a legend. It was a disaster that became a warning for the whole industry. Throttle sensors died, and the computer would throw codes that left trucks sitting on the shoulder with no way to limp home. The hardware couldn't handle the heat and the vibration of the road, and the drivers who trusted Cat the most felt the most betrayed. The reliability they had counted on for years was gone, replaced by a wiring harness that could strand an 80,000-pound rig over a $5 sensor. Caterpillar's failure with Peak sent a shockwave through the industry, but Cummins took a different route. They watched the Cat disaster and realized they couldn't just bolt a computer onto an old pump. Instead of trying to save the old pump design, they built the engine around electronic unit injectors just like Detroit did with the Series 60. The N14 kept a tough 855 family block, but used a computer to hit the EPA targets without killing the throttle response. Mechanics who could diagnose a Cummins just by the sound of the idle or the color of the smoke lost their edge overnight. The instincts that they had built over a lifetime suddenly meant nothing because the problem was hidden in a data stream instead of the iron. In truck stops from Texas to Montana, guys who could rebuild a fuel pump with their eyes closed were now staring at wiring diagrams. Some adapted, but a lot of them didn't. They just picked up a pair of wire cutters instead. The wire cutters were just the start of the fight. What the war inside the cab eventually produced wasn't a revolution, but a loophole that was worth $100,000 to the right buyer. To understand why, you have to look at the math that changed the industry. An engine built to deliver that legendary longevity and be rebuilt forever is a direct threat to the company that manufactured it. Every mile a 3406B runs past its first overhaul is a mile that doesn't generate a new engine sale for a Caterpillar. Every big cam that a specialty shop breathes back to life at 800,000 miles is a hit on the new unit revenue at Cummins. The mechanical era produced iron so durable it was eating the manufacturers alive, and the corporate accountants eventually noticed. That awareness started shaping engineering decisions in ways that had nothing to do with how well the engine actually ran. Modern after-treatment systems don't just clean the exhaust because they also create a massive dependency on the dealership. A diesel particulate filter that needs a parked regen to clear out soot is a truck that can't move 45 minutes on a schedule the driver doesn't control. When a NOx sensor fails and triggers a stage 3 derate, it doesn't care that the iron underneath it is mechanically perfect. The computer sees a bad signal and limits the truck to 5 miles an hour, regardless of the load or the deadline. Fixing that failure requires proprietary software and a dealership appointment, which usually means a tow bill because these things always break at the worst possible time. An independent owner-operator running one truck on thin margins cannot survive that kind of math. Some of these guys went looking for a way around the system, and they found it in the glider kit. A glider is a brand new cabin chassis from Peterbilt or Kenworth built to 2018 specs, but it's wrapped around a fully remanufactured mechanical engine from the 1980s. You get a 3406B bored and honed to 0 miles or a big cam rebuilt with new liners and fresh injectors in a truck with modern air conditioning. The FMCA rules for electronic logs apply to the engine model year rather than the chassis, so a pre-2000 engine in a new truck is exempt. There is no black box and no DDEC reporting, which means no fleet manager is watching your idle time from an office building. Fitzgerald glider kits in Crossville, Tennessee turned that loophole into a massive industry. At their peak, they were moving over 1,000 units a year to drivers who were willingly paying $150,000 for the privilege. They were buying the last legal version of the machine they actually wanted to run. Iron with no black box, no D-rates, no fleet manager watching from a satellite office, a mechanical rebellion with a title and a VIN plate. Then the final door slammed shut. The EPA moved to kill the loophole through new greenhouse gas rules, and the IRS followed up with a massive tax assessment that ended Fitzgerald's operation. It was over. The suits had won. Large-scale production ended, and you couldn't legally build a new glider anymore. But the trucks already on the road stayed there, and the iron hearts inside them kept right on pulling. The mechanical era didn't end because the engines wore out. It ended because the front office found a way to make durability unprofitable. There are still 3406Bs pulling grades tonight, running on nothing but a fuel pressure and mechanical timing. The Jake cracking on the downhill, no fault codes, no DEF tank, no regen cycle, just the fuel rack and the physics of the job. The men who built the digital management systems got what they wanted. An engine the driver couldn't own, couldn't tune, and couldn't fix without a dealership appointment and a laptop. But the 3406B is still out there pulling loads, and the men who understand it are still turning wrenches on iron built before some of them were born. That isn't nostalgia, that's a verdict. If you've spent time in the cab or under the hood of one of these, sound off in the comments. Hit subscribe before you clock out, and we'll see you on the next one.